So we're going to talk here about what we mean by continuity, or saying something that is continuous. And I want you to think for a minute about what we mean when we say something is continuous in the English language. And we're going to pull that into like what we are going to mean by it in math. So take a minute, think about what you think it might mean. All right, so some people notice that it has the word continue in there. And so some people will naturally gravitate towards continuing being to keep going. If something is continuous, it keeps going. And I want to actually bring in another meaning of continuous, and that is basically like that it doesn't have any breaks or interruptions. So if you look up the definition of continuous, forming an unbroken whole or without interruption. And a lot of times when, just sort of without context asked about continuous, there's this ceaseless actually meets with the first definition that it keeps going. When something is continuous, we will say it has continuity. If it is not continuous, we will say discontinuous, or we will say that it has discontinuity. So let's look at some examples of discontinuities, and I want you to think about this, and you can pause the video and see if you could imagine what a graph of a function might look like if it has some discontinuities, keeping in mind that we're thinking about continuity as being something that has no breaks in it or interruptions. So see if you can draw a graph of something that is not continuous. So one idea that you might have is if a function kind of is up here and then all of a sudden it jumps and the output moves to a different place. And as we're thinking about this, we're kind of thinking about the function in terms of like what happens when we run through the inputs of the function. And as I run through the inputs of this function in this way, the outputs seem to be going in some sort of a predictable manner, but then all of a sudden there's this sudden jump that you don't actually, like you end up somewhere completely other than where you think that you're heading. That's one type of discontinuity. And another one that can be like related to this, and it's something that doesn't really show up much or very often. If we're kind of coming along here, but then there's this hole, and for some reason the value of the function is different at that one point. So let's actually say something about both of these. If this is called A, and this is a graph of y equals f of x, we would say f has a discontinuity at x equals a. And again, this is true here. So there's one other kind of picture of discontinuity that you might think of, which is like if a graph has vertical asymptotes, so where the function sort of goes off to infinity when it gets to a certain number. So you might think of like, for example, the tangent function has discontinuity at pi over 2, or let's look at like some sort of a rational looking function. Say I have some function that kind of goes up like this. Okay, and if we call this number a, we say f has a discontinuity at a. Okay, so these are our three basic types of discontinuity, and I'm going to go ahead and name them right now. So this first one, where the output values jump very suddenly, we call this a jump discontinuity. So let me just kind of move this over. So that's a jump discontinuity, which kind of makes sense because the graph jumps at some point. And in this case, what we have This doesn't seem quite intuitive, but it'll make sense later on. We call this a removable discontinuity. And you might be able to guess this third one, what type of discontinuity that is called. See if you can guess. It is called an infinite discontinuity. Now, this is all sort of an informal introduction, and if we can think about what these mean to formalize it, then that will help us move forward to see how we work with discontinuities or continuity. Okay, so thinking about like, what is it about these graphs and these functions that catch our eye as being off somehow, that there's a discontinuity? So one thing that you might notice is, for example, in this particular, in the jump discontinuity, that there's some sort of like continuity and expected behavior to the left of A, and there's some sort of expected predictable behavior to the right of A, but at A itself, it is not, those behaviors are not consistent. Like maybe we can say that the output values for values of x less than A are inconsistent with the output values of inputs of x greater than A. How about if I just say it this way? Okay. And you might notice, like, it doesn't really matter if the value of f at A is here or here or somewhere completely different, if it's some completely other place or not defined at all. It's more about what's happening for x values that are near A and either strictly less than or strictly greater than A. Okay, and in this case, for the removable discontinuity, you kind of see that the output of f at x equals A is not consistent with other outputs for values of x that are near A. Okay, and if we want to think about this sort of informal notion of what the infinite discontinuity looks like, it might be that as x gets close to A, the outputs grow without bound. Let me say grow out of control, since we're being informal here. To formalize this, we're going to actually use the notion of limits, because limits are, in fact, a way of predicting output values. So when I'm looking in this graph here with the jump discontinuity, oops, there was a jump discontinuity right there. There's this prediction that, like, as I am moving along inputs to f, then I can see my outputs kind of climbing, and they look like they're getting right to this y value, whatever that y value is. And that's kind of what, if I say, like, it looks like it's getting close to, I'm really making a prediction that I am going to end up at this y value, but then all of a sudden there's a jump and I end up at a different y value. And so limits are really a prediction. And so this one, like when we're talking about limits, we see that the limit coming in from the right, or sorry, from the left, is different from the limit coming in from the right. So a jump discontinuity is one where the limit, both of the one-sided limits exist, but they're different. Let me write that in words. So the limit as x approaches a from the left of f of x exists, and the limit as x approaches a from the right of f of x exists, but they are not the same limit. So that is what's happening here, and that we can see that that's the mathematical description of what's happening in the graph, what we're seeing in the graph. What we have in the removable discontinuity picture is that both of the left-hand limit and the right-hand limit exist, and they are the same, but they are different from the value of f at a. So we have the limit as x approaches a of f of x exists as a two-sided limit, but it does not equal f of a. And I just want to point out the removable discontinuity would also be a removable discontinuity if f was not defined at a, but as long as the limit as x approaches a of f of x does exist as a finite number. Okay? And this last one, the infinite discontinuity, is basically if the limit as x approaches a from the left or from the right is an infinite limit, so plus or minus infinity. So these are the ways in which we can have discontinuities in a function, and this will feed our understanding of what it means for a function to have continuity at a single point. So let's look at that as a definition, and basically you can kind of see the hints of it already here, that it has to do with, for one thing, a function having a limit as x approaches a finite limit that's well defined, and that it equals the value of the function at that point. We're going to say a function f is continuous at an input value a if the limit as x approaches a of f of x. So I'm going to say if that limit exists as a two-sided limit, and f of a also exists as a finite value, and these two things are equal. Okay, so go back and think about how this is the thing that sort of defines continuity, and those three examples that I gave before show discontinuity. Note that writing this equation actually requires that both sides of that equation exist as finite numbers, and that those two numbers are equal to each other. So we could say it requires that the limit as x approaches a of f of x exists, and this is a two-sided limit, and I should say two-sided finite limit, finite like not infinite, and f of a exists, which is to say a is in the domain of f, and the two numbers are equal. Okay? So there's really, writing that equation does not make any sense unless the left-hand side exists as a finite number, and the right-hand side exists as a finite number, and those two numbers are equal to each other. Okay? So let's look back here, and so in the jump discontinuity case, it fails to be continuous at a because the limit does not exist as x approaches a, as a single finite number two-sided limit. The removable discontinuity fails because the limit does not equal the value of the function at that point, and the infinite discontinuity fails because the limit doesn't exist at that number in a very specific way, which is that at least one of the one-sided limits is infinite. And we should say, like, the jump discontinuity is the limit doesn't exist in a very specific way, which is that the left-hand limit and the right-hand limit are both finite numbers and they're different. All right, so look at a future video to see how to calculate discontinuities in a few examples.